Hello there and welcome to our module on measures of central tendency. Now this is a really important module. You need to make sure you can calculate these measures and you need to be able to interpret them. And these are highly examinable, so make sure you really understand these computations. Let's have a look at our first slide. So our LOS here says calculate and interpret measures of central tendency. Well, I think before we do that, we really need to discuss what is central tendency. If you like, you can think of central tendency as the centre, hence central, centre of a data set. In other words, you can think of it as the average point in a data set. Another way of viewing it is to think about it as being an expected value. Now, we've given you the formula here to calculate the arithmetic mean of a sample of information. Now, when you've got a sample of data, essentially, we tend to use X bar. So this is our sample mean. And that means we've taken a sample of data from the population. Typically, we take sample means and we use them to make inferences about the population, i.e. the population mean. And we're going to do this within hypothesis testing a little later. Now, if we talk about the population mean, we give it a slightly different symbol. It's given the symbol mu, but the calculation is exactly the same. The sum of all of our observations divided through by n. Notice all that really happens is that we use small n when we're talking about sample mean and we use capital N when we're talking about population mean, but actually the computation does not change. Now, chances are you've been calculating means or arithmetic means all the way from your early school days. All we need to do is sum the observations and then divide through by n, and n is the number of observations. Key point with arithmetic mean is we are going to include all observations, and that includes extremely large and extremely small values known as outliers. There is only one arithmetic mean for a data set. And finally, the sum of deviations from the mean. And what do I mean a deviation from the mean? The distance from an observation, so there's our observation, xi, from the arithmetic mean. That's a deviation, so the difference from an actual observation from the arithmetic mean. If we were to sum those for all deviations, we would get a value of 0. In other words, what we're saying is 50% of the observations by size are greater than the arithmetic mean, 50% of the observations by size are lower than the arithmetic mean, and if you sum those deviations, you're always going to come to 0. This has some significance for calculating standard deviation a little bit later. Now, what you need to know is outliers, so extremely large values and small values. In other words, values that are significantly bigger than the mean and values that are really significantly lower than the mean have a big impact on arithmetic means. They have a big distortion on the arithmetic mean, and that can cause our mean to be skewed. So, for example, if we've got one observation that's extremely large, far larger than all of the other observations in our data set, that's going to pull the arithmetic mean upwards. So maybe that arithmetic mean is no longer representative. Same for a value that's significantly smaller than the typical values in the data set, that's going to pull your arithmetic mean down. So with arithmetic mean, we include those outliers, but there is that worry that it could distort our mean. It could skew our mean. And we'll talk about positive and negative skew in a little while later. So what we're going to talk about now is what could we do to limit the impact of outliers on our arithmetic mean. Well, adjusting for outliers, we've got two methods to adjust for outliers in our syllabus, a trimmed mean and a Windsorized mean. Trimmed mean just means we exclude a certain percentage of the biggest and smallest values. So notice with a 1% trimmed mean, we're going to exclude 0.5% of the highest values and 0.5% of the smallest observations. Okay, so therefore, our mean therefore comprises of 99% of the observations, but not the biggest and not the smallest. Well, that's all very good, but that can lead, as we said, to bias. What happens if we've excluded values, okay, and they really do have significance? Well, we've ignored those values, so it could lead to a biased mean. So another way of calculating or adjusting for outliers is to calculate what's called a Windsorized mean. Now, this Still going to have bias, but it's probably going to have less bias than a trimmed mean. So with the trimmed mean, we're just going to exclude outliers. So the outliers are not included, okay, and therefore that's why it's called trim. With a Winsorized mean, we're going to include those outliers, but they're going to be modified. Now, another name for modified outliers is censored outliers. Okay, now the idea is this should give you less bias than simply excluding outliers. So let's have a little look at this. We've got an example of a 90% Winsorized mean. What we're going to do is substitute the 95th percentile value for the greatest 5% of observations and the 5th percentile value for the smallest 5% of observations. What does this really mean? Well, I've put together a little illustration to demonstrate this. Okay, so what I've got is 10 returns here. Okay, ranging from 1%, the smallest value, up to 40%. Now, if we first of all start off by calculating the arithmetic mean, I'm just going to sum those observations. So 1 plus 8 plus 12 plus 15, etc., giving me a total of 172. I then divide that by n, the number of observations, which is 10. 172 divided by 10, that gives us 17.2. Now I'm going to calculate an 80% Winsorized mean. Now you might be wondering where this phrase Winsorized comes from, or Windsor. It just comes from the guy that invented this, a guy called Charles P. Windsor. Okay, so it doesn't mean anything other than his name. So we're going to do an 80% Winsorized mean. What does the 80% mean? Well, we're going to include 80% of the values without any modification. Now we've got 10 observation here, so we're going to include all the values, observation 2, all the way up to observation 9. And notice I've ranked my observations from lowest to highest to do this. So those values, that 80% of observations, we're not going to modify. But what I am going to modify is this value here, okay, the lowest 10%, and this value here, the highest 10%. And what we're going to do is we're going to replace them with the 10th percentile and the 90th percentile. Now, 10th percentile is 8, so I'm going to cross this figure out and I'm going to replace it with 8. And the 90th percentile is this figure here, 23, so I cross this out and replace it with 23. So now when I calculate my Winsorized mean, I'm doing 8 plus 8 plus 12 plus 15, all the way up to my 9th and 10th value, which is plus 23 and then plus 23. Now when I do that, my total becomes 162. I've still got 10 observations, so my Winsorized mean would be 162 divided by 10, which would be 16.2%. Okay, so that's what we mean by a Winsorized mean. Weighted mean. Okay, now a mean which different observations have different proportional influence on the mean. Okay, so what we've actually got here is an example where we're looking at the mean of a portfolio, and we've got a number of assets, asset I, asset 1, all the way up to asset N. So we've got the return on asset 1, return on asset 2, all the way up to the return on asset N. Now what we're then going to do is we're going to weight those means according to the proportion of each asset in the portfolio. So in other words, if asset 1 is 20% of my portfolio, I'm going to take 20% of its return. If asset 2 is 30% of my portfolio, I'll take 30% of its mean return, its expected return. Now, key point is our weights will sum to 1. In other words, 100%, which represents the full portfolio here. Let's have a look at it via an example. So we've got a portfolio here. 50% is equity, 40% is debt, and 10% in cash. And we've been given the expected returns of 12%, 7%, and 3%. So all I'm going to do is take 50% of my stock return, so 50% of 12, 40% of my bond return, so 40% of 7, and then finally 3% of my cash return, so 3% of 10, and then I'm going to sum them together. So here it is. my weighted mean, 50% of the equity return, 40% of the debt return, and finally 10% of the cash return. Sum it up and my portfolio has an expected return of 9.1%. So that's a weighted mean in terms of computing a portfolio mean, and the weights come from the proportions of each asset within your portfolio. But we can calculate other weighted means. Maybe I want to maybe I'm looking at stock returns and I want to give more recent stock returns a higher weighting than older stock returns. So maybe I give it 50% weighting to the return last year, 30% to the return 2 years ago, 20% weighting to the return 3 years ago to calculate my mean return. Okay. Key point though is your weightings have to add up to 1. Just be aware you can, of course, do this on the BA2 Plus calculator. Okay, so you go into stats mode and you can enter your data, 12%, 7% and 3% as the X variables. You can then enter your weightings 50, 40 and 10 as the Y data. Okay, but be careful when you enter weightings in the calculator, enter them as whole numbers and not as decimals. Otherwise, your calculator is going to give you an error message. Okay, so we've talked about our arithmetic mean and we've talked about a bit of dealing with outliers and we've talked about weighted mean. Next measure we have is median. Now, key point with median is it's less affected by outliers than the arithmetic mean. Okay, it's not to say it isn't affected by outliers, but it's certainly less affected by outliers. Now, this is the midpoint of a data set when we rank the data from lowest value to highest value. So half of the observations will be above this point and half below this point. And this can be quite useful. So I was giving a presentation and we were looking at living standards post 2008 financial crisis. And I made the comment that living standards essentially have remained fairly static over the last few decades. And one of my candidates said, but look, mean salaries have actually increased, and indeed they had. But when we looked at the median salary that people were earning, that had remained constant. What was that telling us? Well, it was telling us that the mean was being pulled up by positive outliers. In other words, the highest earners in society had been seeing their wages increase, but overall, the midpoint hadn't really modified. Now, let's have a look. With an odd number of observations, calculating the median is dead straightforward. So in our first example here, we've got 5 observations, 15, 21, 23, 25 and 30. Note we rank them from lowest to highest and we just choose the middle point, which in this case is 23. But what happens if we have an even number of observations rather than an odd number of observations? Now the problem is, of course, with an even number of observations, you are going to have 2 middle points. So in this next example, we've got 6 observations, 15, 21, 23, 25, 28 and 30. So we've got 2 middle points, if you like. So how do we calculate the median? Well, we're going to simply take a straight line average, a linear average of those 2 middle points. So take your 23, 25, add them together to get 48, divide by 2, and we get our median value here of 24. Now, last point we've got there is less affected by extreme values than the mean. So remember, when we were looking at those salaries, or when I was looking at salaries over the last 20 years, or since the 2008 credit crunch, so slightly less than 20 years, the median salary, the median living standards had remained steadfast and hadn't really changed much, but the mean, arithmetic mean wages had increased, telling us we had positive outliers. The rich were getting richer, or the extreme rich were getting richer at the expense of everybody else. So quite useful, the median, less affected by extreme values, outliers than the mean. Next one is mode. Not very excited by mode. It is simply the most frequently occurring value in a data set. So here's our data set, 5, 15, 23, 25, 28, 28, 30. 28 occurs twice. That is the most frequently occurring value, so our mode is 28. But what happens if we had, let's say, another value of 15 here? Well, then we would have 2 modes, 15 and 28, in which case that would be a bimodal distribution. So note that you can have more than one mode. Remember, with arithmetic mean and median, you can't. There is only one arithmetic mean, there is only one median value, but there can be multiple modes potentially. Now we move on to look at geometric mean. This is going to again be a very, very important computation in our syllabus, and we're going to see it again in portfolio management when we calculate time-weighted returns. Okay, so notice our geometric mean is used to calculate periodic compound growth rates. What does compound mean? Well, we're going to invest for the first period. We're then going to invest our initial principal and the returns we made over the first period in the second period. So we're generating returns on reinvested returns, and that means we're talking about compound growth. Now, if our returns were constant over time, so we were making, let's say, a 5% return every single period, then our geometric mean will equal our arithmetic mean. Arithmetic mean would be 5%, geometric mean would be 5%. However, once returns vary over time, then the arithmetic mean will always exceed the geometric mean. Now let's have a look at our periodic compound growth rate. What we're going to do is take 1 plus our return, okay? 1 plus our return is a decimal. So if we had a 10% return for period 1, then this value, for example, would be 1.1. 1 plus 10% is a decimal. If in the second period we had a 5% return, then this value would be 1.05. So we're taking 1 plus our periodic return and multiplying them together. Okay, so we're taking the product of 1 plus the returns. And then notice we're then raising that to the power of 1 over n. Now, if your returns are all annual, then n will simply be the number of annual returns you're linking together. But if your returns were not annual, let's imagine we've got semi-annual returns here. Okay, then you've got to be careful with your n, because n is the number of years typically from start to end. So let's imagine you've got 4 semi-annual returns. Well, 4 semi-annual returns would cover, of course, 2 years. So n would be 2, it wouldn't be 4. Okay, so just be a little bit careful on that. As I said, if you're dealing with annual returns, that's not an issue. Okay, the number of returns is equal to n. But if you're looking at semi-annual returns, then of course, then n is equal to half the number of your semi-annual returns. Okay, so just be a bit careful on that. So we do 1 plus our periodic return as a decimal. Okay, we take the product of all of those and then raise it to the power of 1 over n, n being the number of years from the beginning to the end of the periods we're looking at. Now that will give us 1 plus our periodic compound return, so we then subtract 1 to get the periodic return as a decimal. Okay, so let's have a look at computing our compound growth rate with an example here. So we've got Acme Corporation here, and we've got 3 years of returns. So in the first year, the return is negative, minus 9.34. In the second period, it's 23.45%. And in the third period, 8.92%. And we're going to calculate the average annual compound rate of return. Okay, so 1 plus our annualized compound rate of return is equal to, let's start off with our brackets first. 1 plus, of course, our annual rate of return as a decimal. So, of course, because we've got minus 9.34% in the first period, it's minus 0.0934. In the second period, it's a positive return of 23.45, so 1 plus 0.2345. And in the third period, 1 plus 0.0892, 892%. Now we're assuming, of course, that these are annual returns, and we want to work out the average of those 3 lots of annual return. So we then take the cube root. Okay, now the problem is we can't do that on our calculator if we're using a BA2 plus because it doesn't have a cube root function. But that doesn't prevent us from doing this. Okay, so what we're going to do is do 1 plus our annualized rate of return as a decimal, so 0.9066 times 1.2345 times 1.0892, and then rather than taking the cube root, we're going to raise it to the power of a third, 1 over 3. where 3 is the number of annual returns we're linking together in this example. And of course, raising something to the power of a third is the same as taking the cube root. Okay, so you're going to need to do this. Whilst your calculator does have a square root function, it can't do anything other than square roots. Can't do cube, can't do the fourth root, etc. So let's do this on your calculator. So 0.9066 times 1.2345 times 1.0892, press equals. And you should be looking on your screen at 1.2190. Okay, so if I multiply those together, this is simply multiplying what I've got in the bracket together. I've got a value of 1.2190. Okay, now I need to raise that to the power of a third. Now on your BA2 Plus, you'll see your power of button is directly above the number 9. So press Y to the X, the power of button, and we need to raise it to the power of a third. So the easiest way to do this is to open a bracket above the number of 7. So press the bracket, do 1, divide by 3, close the bracket above the number 8, and you should see 0.333333, which of course is 1/3. Then press equals, and I'm now looking at 1.0682465. So we've rounded that to 1.06825. Now that, of course, is 1 plus the average compound rate of return, the average growth rate, if you like, over that period. Subtract the 1, and we've got an annual compound growth rate of 6.825%. Okay, let me get rid of my ink for you so you can see that a bit more clearly. So there you are, subtract your 1, and you've got 0.06825 as a percentage, 6.825%. Now again, make sure you can interpret this. Having a negative return of 9.34% in the first period, a positive return of 23.45% in the second period, and a positive return of 8.92% in the third period is the same as having 6.825% for each of those 3 years. But remember, it is a compound rate of return. So remember, we're taking our returns, not only our principal, but our returns from the first period, and then reinvesting that for subsequent periods. So geometric, very, very important. Now, strange one that you've probably not seen before, and that is a harmonic mean. This is used, you can see, to find the average cost per share of stock purchased over time if each purchase is a constant dollar amount. Okay, now that's a key assumption in this. So let's imagine that we invest $2,000 each month, and we do that for 3 periods. So key point is we're investing the same monetary amount each period. Okay, so you can see our harmonic mean is calculated as N, the number of purchases of equal dollar amount, over 1 over XI, where XI is the share price at time I. Okay, looks a bit complicated, but let's actually break it down into an example, and you'll see it's really simple, and we'll see what this formula is actually doing. So we've got a client investing $1,000 in shares of a mutual fund at the beginning of each month for 3 months. So we're investing $1,000 month 1, month 2, month 3. Same monetary amount each period. And we're paying $8 per share in month 1, $9 per share in month 2, and $10 per share in month 3. And we want to know, what is the average price we paid per share over those 3 months? Okay, now I'm going to start off with this formula here, because I think this formula over here really explains what's happening. I'm investing a total of $3,000. In month 1, I spent $1,000. Okay, and I was buying shares at $8 per share. So 1,000 divided by 8, that gives me 125. So I purchased 125 shares in the first month. In the second month, I spent $1,000 when the shares were $9. Okay, let's do 1,000 divided by 9. So that meant I could buy 111.11 shares. Let's just assume that we can buy fractions of a share at the moment. Okay, oops, sorry, I put that in the wrong place, haven't I? Let's just shift that across. 111.11. 1,000 divided by 9. So these are the number of shares that I'm actually purchasing. And then in that third month, I'm paying $10 per share and I'm spending $1,000. So that'll obviously allow me to buy 100 shares. So note, therefore, the total number of shares that I could buy is, what is that? 336.11 shares. Now notice what the sum's then doing. It's taking 3,000, the total amount of cash that I've spent, and putting it over 336.11, the total number of shares that I've purchased. So 3,000 divided by 336.11, that tells me my average price per share was 8.926. Now notice we can make this computation more simple by using the formula that we saw on the previous slide. N, the number of purchases, over 1 over the share price. So we made 3 equal purchases here. So N is 3. Okay, so there's our 3. And the price in the first period was $8, so we're going to take 1/8. Price in the second period was $9, so 1/9. And the price in the third period, $10, so take 1/10. Okay, and we get exactly the same answer, 8.926. Notice, in fact, the only difference is both our numerator and denominator are different by 1,000. We didn't multiply through by 1,000 on them. Okay, other than that, it's the same sum. I like to show this first because I think once you've seen this computation here, you actually have a chance of understanding what the harmonic mean is. You can see it simply. But in terms of speed and computing it in an exam, then of course that might be the way to go. Lovely, so that is harmonic mean. Now they like us as well to be able to interpret these, in particular rank them from lowest to highest. Now we're asked to calculate the arithmetic, geometric and harmonic mean of 8, 9 and 10. So arithmetic mean, 8 plus 9 plus 10 divided by 3 is 9. Geometric mean, now when you're dealing with whole numbers like this, it would be simply 8 times 9 times 10 to the power of a third. Okay, so that's exactly what we've done. Again, remember on the calculator, you would do that as 8 times 9 times 10 power of a third. Okay. Didn't add 1. Okay, so we don't need to subtract 1. We only add the 1 when we're looking at decimal returns, and then we need to subtract it to get our geometric mean. Now, what I want you to take away from this is note the geometric mean is lower than the arithmetic mean. And remember, this will be the case as long as these values vary. So in other words, if I've got 8, 8, 8 in each period, okay, rather than 8, 9, 10, 8, 8, 8, arithmetic mean would be 8, geometric mean would be 8, okay? But if they vary, then the geometric mean will be lower than the arithmetic mean. Finally, we're going to calculate the harmonic mean, 3 observations, and we're going to do 1 over 8 plus 1 over 9 plus 1 over 10, and we get 8.926, the lowest value so far. So in terms of order, arithmetic mean the highest, geometric mean in the middle, and harmonic mean the lowest. Again, expect these means to be tested in your examination, so make sure you can compute arithmetic, geometric, and harmonic. Okay, harmonic, remember the average price paid when you're making equal dollar purchases, equal monetary purchases of stock over a period of time. So yes, arithmetic is largest, harmonic is smallest. Okay, now our next LOS says evaluate alternative definitions of mean to address an investment problem. So in other words, we just need to know our different definitions of mean. So arithmetic mean, when do we use this? Well, we use this to calculate an expected value. Okay, a single future observation from a distribution. So if you were asked, what is your best estimate of next year's return, and you've got a set of data to work with, you would calculate the arithmetic mean. Okay, that would be your expected value. That therefore would be your best guess of the return in the next period. So that's our expected value of a distribution. Geometric mean, when do we use this? Well, if we're asked to calculate a compound growth rate over a period. So the compound rate of return or a compound growth rate over multiple periods, then of course that is our geometric mean. Trim mean or Windsorized means, remember we're going to apply these if we've got extreme outliers. So very big Positive values, values that are highly above the mean, or values that are very much smaller than the mean. And we think they are causing our mean in some way to be skewed. Remember, of course, in terms of how things are affected, mean is always affected by outliers more than median, and typically mode is not affected at all. Harmonic mean, our final one here. Of course, we use our harmonic mean when we're looking at the average price paid for shares when we're investing a fixed monetary amount each period. And those periods need to be equally spaced, we should point out as well. Okay, so those are our measures of central tendency. Absolutely critical to make sure you've mastered those for your examination.